Distributed control systems offer many benefits for a wide variety of industrial measurement and control applications. By integrating computer technology into a sound process design, distributed control allows advanced control strategies for improved product quality and consistency, control flexibility, safety improvements, and increased operating efficiency. With its expanded information resources, distributed control also provides greater understanding of the process, history, inventory, and trends. This data can help to disclose how resources such as raw materials, energy, plant equipment, and personnel are being used to produce a product. Let's compare today's technological advances with some of the predecessors of distributed control systems. First, we'll look at feedback control loops and single-loop analog control. Then we'll examine direct digital control and supervisory control. Let's use this block diagram to illustrate the principle of feedback control. Feedback control consists of a single loop with a sensor, a transmitter, a controller, and a final control element. The sensor measures the value of the process variable, and this value is converted into a usable signal by the transmitter. This output signal representing the value of the process variable is sent to the controller, which generates an output signal to the final control element, based on the difference between the measurement and a set point. The final control element is then positioned to return the variable to the set point. This drawing shows an analog control system composed of several single feedback control loops. There is no communication between the individual loops. If a single analog feedback loop malfunctions, the other loops continue to control their portion of the process. Each of the feedback loops is independent. Analog systems concentrate the control instrumentation in control rooms such as this one. You monitor each separate instrument to assess the status and control the process. As you can see, this may be difficult, for there can be a large number of panel-mounted instruments. Sometimes the amount of process information can be overwhelming, and if you step back for an overview of the process, the discrete instruments are difficult or impossible to read. Then, to read a specific instrument, you must move closer and lose the overall view of the process. By having independent loops, early analog control systems maintained reliability, but each loop required separate control instrumentation. On the other hand, direct digital control eliminates the need for separate standalone controllers. We'll use another drawing to demonstrate the concept of direct digital control. Direct digital control replaces the single station controllers with a central computer. Input from the transmitters comes directly to the computer, which is programmed to carry out all process control tasks. The centralized control function makes communication between loops possible, but if a computer malfunction occurs, the entire control system goes down and the process is no longer controlled. Direct digital control can optimize, model portions of the process, or perform more sophisticated control functions not available with single-loop analog control. However, due to the complexity of programming the computer for direct digital control, programming costs are high. In addition, because DDC depends totally on a central computer, a backup computer may be necessary to prevent downtime. Redundant computers can add considerably to the costs of DDC. Significant advances in control technology were achieved with the development of direct digital control. The computer can be programmed to control many different applications. It also facilitates creation of a database, expanding reporting and recording capabilities. And a computer console replaces the array of instrument panels found in analog single-loop control systems. The operator can use the console as a centralized window to the process and get an overall or a close-up view. Another control method that combines the advantages of single-loop analog control and DDC is supervisory control. Like direct digital control, it is structured around a central computer. But all control is carried out by the controllers, and the central computer generates set points and other operating parameters for the controllers. If the computer fails, the controllers maintain control at the last set point value. So, supervisory control takes advantage of the digital features of direct digital control, but is more reliable since the control functions are contained in the analog controllers. All of the advantages and features of direct digital control, analog control, and supervisory control are combined in distributed control. Let's use this drawing to see how characteristics of the three predecessors are incorporated into distributed control, or DCS for short. Control subsystems perform all control functions that are found in the central computer in direct digital control, getting input from the sensor and sending output to the final control element. The console is the means for operation. The data processor loads and stores system configuration. If failure occurs in a subsystem, other subsystems will not be affected. But like direct digital control, all information about the process is available through the console. You adjust control parameters and monitor all loops of the control system from the console. Like direct digital control, a computer is responsible for the control functions. But in DCS, each of the control subsystems is a computer that controls a number of loops, both continuous and discrete. Microprocessors within the control unit are configured via menus to execute process control functions. Distributed control systems are an evolutionary step beyond supervisory systems and combine the standalone control qualities of analog single-loop control systems with the computerized control functions of direct digital control. Process control is distributed in several ways in DCS. There is functional distribution of control. Each control unit is responsible for control of only a portion of the entire manufacturing process. Because of the functional distribution, if one controller fails, only those loops controlled by it will be affected. And if your process environment allows, there can be geographic distribution. The control subsystems can be located near the process, which reduces the amount of wiring that must be run to the control room. The consoles can also be distributed geographically, located where they are most appropriate. In this program, you'll see what the functional and geographic distribution of distributed control can mean for you. To do this, we'll examine basic hardware components of a distributed control system. Then we'll look at the features and capabilities of distributed control systems in terms of control, operation, and information processing. Using some specific examples, we'll also examine the benefits that a distributed control system can provide, such as safety, flexibility, more efficient operation, and increased process information. The benefits of DCS can help you to safely produce a higher quality product at a reduced cost. Now, take a moment to review what you saw in this segment. We saw earlier how control functions can be distributed in DCS, while process information is readily available to any user. In this segment, we'll look at the hardware components of a distributed control system and see how they work together to provide control. Let's take another look at our simplified DCS drawing. A distributed control system is made up of a few basic hardware components: control subsystems, console subsystems, a data processor subsystem, a gateway interface subsystem, and a distributed communications network, often called a data highway, which connects the subsystems. Although each manufacturer may have different components, the general arrangements are similar. Let's look at the control subsystems first. Manufacturers use a variety of names to designate this unit. Depending on the supplier, the control subsystem can be called a remote control unit, a subsystem, a node, or a control cluster, to name just a few. But regardless of the name, a control subsystem's task is to control multiple inputs and outputs. One control subsystem can directly replace the controllers, either analog or digital, that previously controlled those loops. The control subsystem contains a series of I/O modules that are selected to perform such functions as receiving discrete or analog input from sensors or transmitters, signal conditioning, and producing output signals that position final control elements. And the control subsystems in a distributed control system also use controller modules to execute all control functions. Another major hardware component is the console. Consoles serve as an interface for different functions. The consoles serve as an operator interface, where an operator can monitor the loops of the process control system using different screen displays, and as an engineering interface, where an engineer can design and configure the control system and try out new control schemes. Consoles can also support maintenance personnel with self-diagnostics messages and diagnostic displays. The design of console subsystems varies according to the manufacturer. Some systems have different consoles for different functions, while others, such as this system, have a universal console where different functions are supported with a single console. An access code limits the type of information available to the user and is based on his functional needs, whether operations, engineering, maintenance, or management. These universal consoles maintain system security by assigning separate access levels to different personnel. Standard consoles like this can also be used as direct backups. For example, a console dedicated for engineering use can take over as an operator console if necessary. Another DCS component is a universal gateway. It enables incorporation of other computerized devices, such as programmable logic controllers, personal computers, and mainframe computers. With the help of the gateway, a mainframe computer, for example, can upload information to plant management and company headquarters. The gateway can also be used to upload and download process and control information and instructions to other independent devices. Regardless of the specific type, interface devices such as the gateway facilitate communication between different measurement, control, and engineering systems, or between the control system and personnel. The data processor subsystem is a multi-purpose information processing device used to load and store the database and system-wide configuration functions. Linking all the hardware components of a distributed control system is the Distributed Communications Network. The Distributed Communications Network, or DCN, makes communication between the components of a distributed control system possible. It can also be called a data highway. On it, data bits travel serially from component to component. The control subsystems and the consoles can send data on the DCN to other subsystems and also request data from it. There are a number of protocols governing how data bits are transmitted. In the past, data communication standards have been proprietary. However, trends seem to indicate that the industry is moving toward open system standards with efforts such as MAP and Ethernet. Data highways can be made of either electrical wire cable, such as twisted pairs, or coaxial cable, fiber optic cable, or microwave. In all cases, the DCN is a global highway that runs from the control room to collect data from the local highways at collection points. It can be either a continuous ring, like the one shown here, or linear, and it is often redundant. It functions as the common artery of information between the hardware components. Distributed control, then, allocates control functions between the different components, allowing them to control with great reliability. The control subsystems are responsible for process control functions, and the consoles provide the means for system monitoring and modification. To reduce risk of loss of control, hardware component redundancy is selectively incorporated into their design. Redundancy is provided by duplicate equipment. Duplicate equipment that is most often standard in DCS are control subsystem modules, such as these shown here, DC power supplies, and data highways. Depending on the manufacturer, other redundant components may also be standard or may be available at an additional cost, such as the operator station, including the CRT terminal and the console subsystem modules. Printers may also be redundant. Most often, redundancy is used to back up electronic functions that provide critical control outputs. For example, in this controller subsystem, all control hardware and software, including the I/O, is fully redundant. Strategies for redundant control depend on the supplier and your application. In most cases, however, redundancy is most effective when control is transferred automatically, requiring no action by the operator. For example, a redundant control unit would automatically take over if the primary unit fails. Thus, by delegating control functions to the control subsystems, and by including functional redundancy to prevent or reduce the possibility of loss of control or the loss of the window to the process in the event of failure, a distributed control system creates a reliable means with which to control a process. In the next section, we'll look at some of the control and operation features of distributed control systems. Pause now to review the material covered in this segment. A distributed control system is basically a communication network of computers. With this design, it can offer a broad range of features in the areas of control, operation, and information management. We'll examine the features of distributed control systems in the next two segments. Let's begin with the control and operations capabilities. Later, we'll look at the information management features. As we saw earlier, the major hardware components of a distributed control system are the control subsystems and the consoles. These components are the source of the many control and operations capabilities of distributed control systems. First, let's look at the control features of a typical system. To help illustrate these control features, let's take a closer look at how a control subsystem functions. We'll begin with the power supply. The power supply, as the name implies, provides different power levels to the unit and its modules. There may be several different power supplies to supply power to the control subsystem module circuitry, to the control subsystems themselves, and as backup. I/O terminations, shown here, connect process variable signals to the modules in the control subsystem and provide signal conditioning. The modules in the control subsystem can provide configurable control. Let's look at how modules provide this feature now. Individual modules are responsible for all the control functions. There are two functions served by modules in a control subsystem: control functions and input-output functions. An I/O module may be used to condition a thermocouple signal to be compatible with the input requirements of modules that perform control functions, for instance. A control module receives the conditioned signal, then generates a signal to position the control element. A control module can encompass a full spectrum of applications, from control of continuous processes to batch sequence operations. By selectively choosing and grouping discrete modules, you can create many different control schemes through software. The configurable control feature enables you to use distributed control for advanced control strategies such as cascade, ratio, and feed-forward. In distributed control, no conventional controllers are used. Instead, microprocessors and associated software perform the same control functions as hardwired controllers. Let's look closely at a module to see how it provides this configurable control. A module is made of computing circuitry on pre-printed circuit cards that are held in a card file. It contains central processing units, or CPUs, permanent read-only memory, registers where processing takes place, and buses, which carry information to other units. It is memory that enables a module to act like a controller. One way to understand how module memory is used in DCS is to think of it as a library. The module uses the special resources in the memory library to execute special control functions. Let's use this drawing to look more closely at memory, where the special control functions for a module are located. Within memory are libraries of pre-programmed algorithms and control strategies, such as PID control, summing, logic, and mass flow, to name some common ones. There are many more algorithms that encompass all kinds of control functions. Modules receive inputs representing the value of the process variable and then refer to the algorithms in memory to carry out their assigned functions, like you'd refer to procedure books. Because they are software functions, algorithms can be connected in ways that are difficult or impossible with hardwired devices. So the microprocessors in modules enable them to provide configurable control. Because a control strategy is simply algorithms and modules joined electronically, its configuration can be set up or changed at any time. Manufacturers supply configuration software with which an engineer can build a desired control system. The engineering interface is used to configure the control system. In some systems, a personal computer can be used for configuration. In others, the console may be used for configuration. Configuration software is standard with most systems. It provides the engineer with templates from which to configure the control functions. Templates serve as high-level fill-in-the-blank forms. These templates are used to select modules and algorithms and to designate the addresses of inputs and outputs for specified tags. Most template packages are menu-driven and offer prompting and online help. And most template packages also create documentation automatically. Some systems also allow you to program in a high-level programming language. Some manufacturers have developed their own sequential programming languages. So, distributed control's microprocessor features and software make configurability possible. In addition to the control features, distributed control also has significant advantages for operation and maintenance. Consolidated operation, CRT-based displays, and self-diagnostics are the most notable. Let's focus on the consolidated operation feature now. Because DCS distributes functions, the consoles do not need to be located near the control subsystems. Consoles can reside anywhere in the plant, even in non-ideal conditions if they are field-hardened. The consoles are the interface through which the system is operated, serving as a complete control center for the operator. The consoles make possible centralized operation of the entire process from one location. The console can be used to make changes to the process based on information that is displayed. A variety of devices can be used to make these changes, such as a touch screen, a mouse, a trackball, or a keyboard. Using the console, you can control the process in manual or automatic mode. To change the set point value of a function, or to change the output value of a function. Alarms are communicated and acknowledged through the console as well. Because they can be distributed between more than one console, certain alarms can be viewed by designated personnel, or one console can display all alarms. Another feature of distributed control is the CRT-based displays used for monitoring the process. In DCS, the rows of panel-mounted analog instruments are replaced with a screen that provides concentrated information. Several different displays are available to operators. For example, the CRT screen can graphically display process conditions such as dynamic tank levels. So the screen is a window on the process. Some of the displays available are graphic displays, like the one shown here, which use lines, symbols, and text to illustrate the process or a portion of the process. They can be interactive in nature and can be updated constantly. Portions of the process display may change color or shape to indicate a change in the process. A detail display is often called a tuning display, for output control and tunable parameters can be manipulated from this screen. Detail displays also provide measured values, set point values, and output values of a tag, as well as other information on parameters. A group display provides information about tags that are grouped functionally. A tag may be a PID controller, for example. This group status display shows the process variable, the set point, and the percentage of output. An area display gives an overall view of several related function groups and shows the deviation from the set point. An area status display is shown here. An overview display shows a global view of the entire process. It can provide access to graphic or alarm screens for several different areas. The CRT can also display trends that are similar to chart records in that they show a profile of a process or control value over time. The number of trends that can be displayed varies with the supplier, but usually they range from 1 to 4 variables per chart. Often trends are available for varying time lengths. Alarms are immediately available throughout the range of display screens and flash or beep until acknowledged. They can appear in area, trend, and graphic displays, or in summary form as this one does. Depending on the supplier and your configuration of the control system, alarms can also be enunciated, and they can be printed with the name of the tag that is out of range, along with the date and time. An alarm can also be shown visually on the CRT display. In this example, the flashing box signifies the alarm. When you access this box, you'll be taken to a screen with more detailed information about the alarm. In addition to the process operations displays, the console can also display self-diagnostics that can assist maintenance personnel. Circuitry within the control subsystem modules and consoles of a distributed control system is checked continuously. Whenever a fault is detected, a diagnostic indicator displays on the CRT screen of the console. By accessing the indicator, you can again get a screen of more detailed information. Self-diagnostics allow you to pinpoint a possible fault from the control room. The probable cause can be identified, and then you can narrow down the problem and correct it. So, as we've seen, the operation and maintenance of distributed control systems is consolidated at a console. CRT-based displays allow process monitoring and control and fault diagnostics from a single screen. Control is configurable, with discrete modules providing all control functions within the control subsystems. The modules refer to algorithms within their memory for specific control instructions. Control can be configured to fit a variety of control schemes. In the next section, we'll focus on the information processing features of distributed control. Stop a moment to review what we've covered here. In the last segment, we looked at the control and operations capabilities of distributed control systems. In this segment, we'll examine the information processing capabilities of DCS. These features are alarm and event logs, historical records, both archived and hard copy reports, and the capability for statistical process control. To begin, let's look at this simplified distributed control system illustration again. While control is distributed functionally and can be distributed geographically, information retrieval and processing functions are at a single location. All information from the control subsystems can be brought to a single point via the data highway. Data retrieval, along with the functions of distributed control, makes it possible to create and maintain a database. A database manager manages and manipulates this data and permits access of it by entering the desired tag number. The database manager, and the data processing subsystem together can provide you with information about the process and its control in different formats. Let's begin by looking at one of these formats, the alarm and event logging capability. DCS can log alarms and events from its database. Depending on the system, logs of alarm or event messages can be printed automatically. Another feature is historical recording that can archive trend information and alarm and event information. Historical records can be stored permanently and can also be transferred to a variety of removable media. The historical trend feature can be particularly useful for comparison purposes, such as yesterday's production with today's, or summer energy usage versus winter usage. Historical alarm and event records can help in the analysis of a process upset, for example. DCS systems can also create reports on request at regular intervals or batch reports. You can schedule a regular report to print daily, weekly, monthly, by shift, or at any other desired interval. And reports can be generated on demand by operators. Like historical records, reports can be archived by storing them to disk, and they can be printed on a system printer. A printer can also be used to produce hard copies of operating and repair logs and other records and reports. Reports can also be displayed on the CRT. Reports such as these can be used by management to monitor product quality, production costs, and other production information. For example, inventory control reports can be used to generate purchase orders for raw materials on an as-needed basis. Energy usage reports can be generated to monitor the amount